Chapter 17, Sampling Distribution Models. The sampling variability is the expected variability from one random sample to another. It's also known as sampling error. Random samples yield different samples and different outcomes. Sampling distribution is the theoretical distribution of statistics over all possible samples for the same sample size. The sampling distribution model is used because it's very difficult, if not impossible, to see all the possible samples. So this model is used as a practical way of describing the theoretical sampling distribution. In an earlier chapter, we talked about the normal model with a mean of mu and a standard deviation of sigma. Now here we're looking at the normal model specifically for proportions, where p is the mean and the square root of p times q divided by n is the standard deviation. P represents the proportion of successes, q represents the proportion of failures, and n is our sample size. So when does the normal model with mean of p and standard deviation square root p times q divided by n work well as a model for the sampling distribution of a sample proportion? Well, there are assumptions and conditions that you have to check. So we have the independence assumption, and that says that the individuals in the sample must be independent of each other. Now you cannot know if this assumption is true, but you can check two conditions to see whether the data were collected in a way that makes this assumption reasonable. You have the randomization condition. If it's an experiment, the subjects are randomly assigned to the treatments. If we're working with a survey, then a random sample that is representative of the population. The other condition that has to be checked is the 10% condition, which says that the sample is at most 10% of the population. The other assumption that we have to consider is the sample size assumption. So the sample size n must be large enough, and we use the following condition to check the sample size. We have the success-failure condition. So that says the sample size must be large enough that we expect to see at least 10 successes and at least 10 failures. If that condition is met, then our sample size assumption is met. So let's talk about the sampling distribution model for a proportion. Now, provided that the sampled values are independent and the sample size is large enough, the sampling distribution of p hat can be reasonably modeled by a normal model with mu p hat equal to p and the standard deviation of p hat equal to the square root of p times q divided by n. Let's look at an example of using the sampling distribution model for proportions. The Centers for Disease Control and Prevention report that 22% of 18-year-old women in the United States have a body mass index, also known as a BMI, of 25 or more. Now that value of 25 or more is considered by the National Heart, Lung, and Blood Institute to be associated with increased health risks. As a part of a routine health check at a large college, the physical education department usually requires students to come in to be measured and weighed. This year, the department decided to try out a self-report system. It asked 200 randomly selected female students to report their heights and weights. Only 31 of these students had BMIs greater than 25. So continuing with this same example, the question is the proportion of high BMI students unusually small? Okay, so they told us that the population is 22%, and we had 200 students where 31 of them had a BMI over 25. Okay, so what we're wanting to know is that unusually low? Now, the first thing that we have to do is we have to check our assumptions and conditions. So the first one is our independence assumption. And so for our independence assumption, we have to check these two conditions. So the first one is the randomization condition. The 200 female students were randomly selected. They told us that in the problem. In the problem, they said that the 200 students were randomly selected. So we're going to take them at their word that those students were randomly selected. So that condition has been met. The 10% condition. 200 female students is less than 10% of all female students at a large college. Okay, that makes sense. So both of those conditions have been met. Therefore, our independence assumption has been met. The next assumption we have to look at is our sample size assumption, and we have to check our success-failure condition. Okay, so our sample size was 200, so our n equals 200, and our population parameter p is 0.22. That's the 22% nationally that are above the 25 BMI point. Our q is 1 minus our p, so 1 minus 0.22 gives us 0.78. Okay. Now we have to check our success condition here. So n times p, which is 200 times 0.22, that equals 44. And our failure condition, n times q, equals 200 times 0.78. That gives us 156. So to satisfy that condition, both our successes and our failures have to be above 10. Well, 44 and 156 are both greater than or equal to 10. So therefore, our success-failure condition has been met. And because that condition has been met, our sample size assumption has been met. So both of our assumptions have been met. So therefore, it is okay to use the normal model. Continuing with our example, our observed proportion, p hat, is equal to 31 divided by 200. Now the 31 are the 31 people from the sample that had the high BMI, and our sample size was 200. So to get our p hat, we take 31 divided by 200. That gives us 0.155. Now our expected value is 0.22 because that's our population parameter is 22%. So we would expect it to be about 0.22. Our standard deviation of p hat is our p times our q divided by n, and then we take the square root of that. That gives us 0.029. So now we have to calculate a z-score. So our z is equal to p hat minus p divided by the standard deviation of p hat. And that gives us negative 2.24. So our z-score is more than 2 standard deviations below the mean. So yes, the observed proportion does appear to be unusually small. So remember, the farther you are away from the center of your normal distribution, the more unusual your data point is. So we are more than 2 standard deviations below the mean, so that would appear that our data is unusually small. There's a fundamental theorem of statistics known as the central limit theorem. And the central limit theorem says that the sampling distribution model of the sample mean and proportion from a random sample is approximately normal for large samples. This is regardless of the distribution of the population, as long as the observations are independent and collected with randomization. Now, regardless of the population distribution, the means of repeated samples will tend to follow a normal model as the sample size grows. If the sample size is large enough, the sampling distribution of y bar can be reasonably approximated using a normal model. For our central limit theorem, we also have assumptions and conditions. There's an independence assumption. It says the sampled values must be independent of each other. Now, once again, we cannot check this directly, but we can check it through the 2 following conditions. The first one is the randomization condition. The data values must be sampled randomly. The second condition is the 10% condition. So the sample size should not be more than 10% of the population. We also have this sample size assumption. So the sample size must be sufficiently large. Okay, so what is large enough? Okay, if the population is unimodal and symmetric, a fairly small sample size is okay. If the population is strongly skewed, then a larger sample size is needed. So think about that. If you start with a population that's already unimodal and symmetric, it's not going to be very difficult to get a sample that's also unimodal and symmetric, so you would not need to sample that many data points. Now, if your starting point, your population is strongly skewed, you can still get a sample that is approximately normal. It's just going to take a little bit larger of a sample size in order to accomplish that. The sampling distribution model for a sample mean. When random samples of size n are drawn from any population with the mean of mu and the standard deviation of sigma, the sample means y bar have a sampling distribution with the same mean mu, but whose standard deviation is sigma divided by the square root of n. Now, no matter what population the random sample comes from, the shape of the sampling distribution is approximately normal as long as the sample size is large enough. And the larger the sample used, the more closely the normal model approximates the sampling distribution for the mean. Let's look at an example using the central limit theorem for means. So a college physical education department asked a random sample of 200 female students to self-report their heights and weights. But the percentage of students with body mass indexes over 25 seems suspiciously low. This is what we talked about in example 1 in this chapter. So one possible explanation may be that the respondents shaded their weights down a bit. Now, the CDC reports the mean weight of 18-year-old women is 143.74 pounds with a standard deviation of 51.54 pounds. But these 200 randomly selected women reported a mean weight of only 140 pounds. So our question here, does the mean weight in the sample seem exceptionally low, or is this just random sample-to-sample variation? Well, let's check our assumptions and conditions. So first we have our independence assumption, and our first condition in that is our randomization condition. So we were given in the problem that the 200 female students were randomly selected, so that condition has been met. The 10% condition. 200 female students is less than 10% of all female students at a large college. That condition has been met. So now we can say that our independence assumption has been met. Now our next assumption is the sample size assumption. And we have to look at our large enough sample condition. So the distribution of college women's weight is likely to be unimodal and reasonably symmetric. Now remember, it doesn't have to be perfectly symmetric. Throughout this course, we've been talking about approximately symmetric. So this is going to be approximately unimodal and symmetric. So therefore, it is okay to use the normal model. The mean weight from my sample was 140 pounds. My expected Y bar is 143.74 pounds, and my standard deviation of my Y bar is my sigma divided by the square root of my n, which is the 51.54 divided by the square root of 200. So that gives me a standard deviation of my Y bar of 3.64 pounds. So now I want to calculate my z-score. So I take my sample mean of 140, subtract off my 143.74 and divide by my 3.64. That gives me a z-score of negative 1.03. So my z-score is 1.03 standard deviations below the mean. So considering the normal model, the sample mean weight is not extremely low. We're only just about one standard deviation below the mean. Okay, that is not an unusual value. So that's why we say considering the normal model, the sample mean weight is not exceptionally low. It's not an unusual data point.